Morning, everyone, again. So I've told you yesterday all I wanted to say about graph alignment, which is why I chose a different subject for today. I'll be telling you about distributed optimization with an emphasis on operation in an asynchronous mode and under time delays. This is based on joint work with a bunch of collaborators, which I won't list now. The general context is that we want to do a distributed learning. So it's an extension, if you like, of the popular notion of a federated learning. So we have agents that pool their resources in order to solve a learning task. So their resources would be their data. They have their own data sets, each of them, and they also have compute and communication resources each. And so we'll be mostly talking about solving a supervised learning problem, trying to learn a common model that fits the collective data set of all the agents. There are variants of interest where instead of having just one model that is going to be shared by everyone, you want to personalize the model to the needs of each of the agents, or you want to try and solve a non-supervised learning problem. But today I'll focus on supervised learning. And the typical constraints you might have will be on the time it takes, on the energy you spend on the task, and maybe on the privacy you compromise by sharing data. I won't be talking about privacy, but this is an active topic in this area. Okay, so to be more specific, we'll have a collection of agents indexed by U, each of them holding their own private data set, which is a collection of vectors, so theta u1 to theta u and u. And collectively, they search a model that is a vector x star that is in d dimensions, say. And the paradigm in order to fit their model will be to minimize the empirical risk. So the empirical risk will be the sum over all data points of the corresponding loss evaluated at that data point and at the corresponding model. You can recast that as trying to minimize the sum of our users of a function f sub u associated to the user of the model x by having the empirical risk of that user's data set for function f sub u. Okay. And so we want to know how fast we can do that, how cheaply, number of communications and number of computations. Privacy I won't talk about today. We also want to identify algorithms that will solve the problem in with good performance. So I'll be starting by saying quite a few things about the synchronous setup because it's simpler and it allows to set the scene, introduce the notions that are of interest. And then after that, I'll move to the asynchronous case where we don't have synchronized updates. And I'll finish by telling you about how we try to handle time delays in all the operations involved. Okay, so the synchronous framework. So our network will be modeled as a graph. So the vertex set will be the agents themselves, and edges between the agents representing communication links between them. As before, we are looking for model X star that minimizes the sum of the individual agent functions f sub u. And we'll assume nodes can compute gradients of their local functions. And I'll be making good use of duality. So I'll be also assuming agents can compute gradients of the dual Fenchel-Legendre convex conjugate function f star, that is the dual of their own private function. So defined as a supremum over x of lambda scalar x minus fu of x. On top of those computation primitives, they can communicate with their neighbors in the graph. Okay? So as a guideline, we can focus on a special case where f sub u is the square distance between the model and some data that is specific to the user. And in that case, the problem is known also as the network averaging problem. because we know readily that the solution of the minimization we are trying to do is to take X star as the average of the private vectors held by the agents. And that's a problem that's been studied quite a bit in a distributed computing community, where the even more special case that I'm describing here was studied. So you have in some distributed systems, such as peer-to-peer networks, a need to infer how large is the network, because you have not the full knowledge of the network. So one way to do that is to have one specific agent, U note, initialize a network averaging problem with its own private value being 1 and the others having 0 as their initial value. So you run the averaging problem, and then you end up by having computing in the reciprocal and of the size of the network. Okay, so the synchronous operation we'll assume is as follows. We'll have discrete steps T, at which nodes can compute some gradient and then communicate with their neighbors. And time to compute a gradient will be tau comp, and the time to communicate with neighbors will be tau comp. So these will be our parameters. And to be more specific about communications, which we also refer to as a gossip steps, we'll assume that in a given step, the users feed a vector into the communication primitive. So xv for user v, a vector in RD. And then each user u would receive a linear combination of the input vectors of its neighbors. So specifically, it receives a sum over v of luv xv, and will make a number of assumptions on this matrix L. We'll assume it's symmetric, semi-definite positive. We'll also assume its kernel consists of constant vectors. And finally, we'll assume that the entries of this matrix are non-zero only if there is a communication edge between the corresponding two agents. And actually, you want to think of the Laplacian matrix of the graph as a matrix L that satisfies those assumptions. In particular, it will satisfy this assumption that its kernel corresponds to the constant vectors if the graph is connected. Okay, so I guess you have already seen the Laplacian matrix of a graph, so that's formally defined by this expression. And we'll also deal at some point with a weighted Laplacian matrix where we'll have some weights on the edges. And that's just a variation. Okay. So how are we going to measure the hardness of communicating? Yes? That's what we'll refer to as the gossip matrix, indeed. Yeah, so there are two conventions. Either you take this as the gossip matrix or identity minus this as the gossip matrix. And so if you want it to be doubly stochastic, you would rather have the identity minus some multiple of L. So the two conventions coexist. Okay, so hardness of communication will be measured by what we call the condition number of matrix L. So its spectrum is given by its eigenvalues lambda I of L. So starting with lambda 1, the smallest one being equal to 0. That corresponds to the kernel consisting of the constant vectors. And so the condition number for us will be the largest eigenvalue lambda n divided by the second smallest lambda 2. And as an example, if you have a complete graph where everyone can talk to everyone directly, kappa com will be equal to 1, this condition number, so which means it's easy to communicate. In contrast, if you have a cycle with n vertices, the kappa com will be order n squared, so it's hard to communicate on a cycle. It's much more expensive as we will see. And then we'll make strong regularity assumptions on our individual functions. We'll assume that these are convex, and more than that, we'll assume they are alpha strongly convex and beta smooth. In other words, we'll assume that the Hessian matrices of our individual functions are sandwiched between alpha times the identity and beta times the identity for the semi-definite positive order. And so as is customary in convex optimization theory, the hardness of optimizing those functions is then measured by the ratio beta over alpha, which is the condition number of those functions. And so again, as a guideline, if you think of the network averaging problem, then alpha equals beta equals 1. So the condition number is 1. So the hardness is not on the functions, but rather on the network. Okay. So let's see how we can do that. And we will go dual. And in order to do that, let's first rephrase a bit the objective. So I'll rephrase it as follows. I'll assume now my argument is a matrix of column vectors. Each column vector corresponds to a model that is held by one agent. And so I'll have as an objective function capital F of that matrix X, which is the sum of our agents of their evaluation through their function F sub I of their model Xi. And we want to minimize this F under the constraint that all models are the same. And so it's convenient actually to capture this constraint by saying the matrix X times the square root. You'll see why I put a square root here in a minute. The square root of this L matrix equals 0. So because of our condition on the kernel, this captures exactly our equality constraint. Okay, and so to go dual, now instead of solving this primal constrained optimization, we'll look at the dual convex problems, so which boils down to be a maximization of minus the Fanchel-Legendre conjugate of this capital F, evaluated at a matrix of coefficients lambda times square root L. And so this can be massaged a bit in a nicer form. So because of the additive structure of capital F, the convex conjugate also can be written down as a sum. So it factors this way nicely. And what is nice about the dual formulation is that it combines in a crisp manner the hardness of the functions and the hardness of the networks. As follows. So if I call G the function I'm trying to minimize here, so f star of y square root L, then a bit of analysis shows you that the condition number of this matrix, so the ratio of the largest and smallest eigenvalues of the Hessian, these are going to be upper bounded by kappa comp times kappa com, so the two condition numbers for communication and computation I was considering. So we have some good handle on the hardness of this dual problem. And now let's see how to solve that. So let's start with a basic solution in the textbook on convex optimization. So we'll start with a first order gradient descent. So that reads like that. Lambda t plus 1 would be lambda t minus some gain parameter times the gradient of G, so which reads gradient of f star at lambda t times root L times root L. And so change of variable will make that look much nicer if we write lambda root L as yt. Then we rewrite this as yu of t plus 1 for user u is yu of t minus eta sum over v of luv dual gradient f star v evaluated at yv of t. So we see that this dual formulation is tailored to work well with our communication primitive. And so now if we take the textbook result on first order gradient descent, we will see that, so here with this dual representation, the model for user u would be the gradient of its f star u function at its parameter yu. And basic gradient descent theory tells us that the error between the optimal model and the estimated models as seen by the users, the quadratic error, decays geometrically with the number of steps, with a critical time for this geometric decay that is given by the condition number that we had previously. So in other words, we reach a precision of order epsilon in a number of steps that scales like log 1/epsilon times the condition number times how much it takes to complete one step. So it's tau com plus tau com. Okay, so that was the first result in a convex optimization series. So now we go to the next chapter in the textbook, and we do accelerated optimization. So we do, for instance, Nesterov scheme based on two sequences. So now our agents maintain not one, but two vectors. And so the first vector yu is updated thanks to the same logic as previously, but based on the second vector zu and the inputs zv. Whereas the second vector zu is updated as a linear combination of the last two values of the vector yu. Okay? Yes? Sorry?
Change if you replace the root L by L. So what's the motivation? Is it does a dual change because of that, or that representation?
Actually, we do the analysis on the first formulation without the change of variables. And then we can claim results thanks to the classical analysis without the change of variables for the version with the change of variables, which is much more natural to implement.
No, I didn't understand. So I was talking about the primal formulation.
Yes.
So there's a square root L, which is equivalent. I mean, the problem would not change if you change the square root L to L because it's the same constraint.
Yeah, it would be equivalent. Exactly.
So what's the advantage?
The advantage is exactly in the change of variables.
Oh, because now
this is the whole point of taking a square root. Indeed, you could take L squared. This would be the same problem. The constraint is the same, but expressed with the square root L is much nicer for the change of variable.
Okay.
Yes. You pay a constant in the big O, but then it is a standard thing to do. Yes. Okay, so basic theory of Nesterov's accelerated scheme tells you that if you pick the gain parameters correctly in this two-sequence update, then you'll have a very similar guarantee as previously, except that you can replace the condition number by the square root of the condition number. For instance, if you take network averaging on a cycle with 100 nodes, you go from 10,000 for the condition number to 100, so an improvement by 100, which is significant. So in other words, well, those of you who are experts in optimization know that acceleration does matter. Okay, so one last thing I want to tell you about the synchronous framework before I move to the asynchronous framework is some finer optimization we can do on this scheme. So far, I have assumed we do one step of computation and one step of communication. There is no requirement to do that. You can be more flexible. So for instance, you could communicate several steps for one compute step. And so for instance, if you call upon your gossip operation twice, you feed the input vectors once, you get the output, you feed it once more, then you would multiply not by L, but by L squared. And so by doing several steps of that, you can in fact multiply by some polynomial of the matrix L. And it turns out this can be fruitful. So there is a polynomial that is particularly useful for us. We can construct a polynomial of the matrix L that is given in terms of Chebyshev polynomials. So the precise formula is here. And the reason for doing that is as follows. Thanks to precise knowledge we have on Chebyshev polynomials, we know that if, say, we had a bad condition number for communication, and if we pick Chebyshev polynomial in here of a degree that is order the square root of this condition number for communication, then the new condition number for the matrix pk of L becomes order 1. So we shrink this quite rapidly in a square root kappa com steps of communication. We go down from kappa com to order 1. So if I plug that in the previous result, I have a new global condition number that only involves the computational condition number. And then I replace one step of communication by square root kappa com steps of communications. So what's the big deal of moving around this square root kappa com from the outside of the bracket to inside? Well, if it's very long to compute, then it can make a significant difference. And I guess the main point was that you cannot, in general, improve upon that result. That's as good as it gets, because we can find nasty functions and nasty networks on which this is really, this cannot be improved upon. So these bad networks would be line networks. And we take bad functions which are constructed from the worst case functions in the analysis of the Nesterov acceleration. So you have those functions for which you cannot do better than the Nesterov acceleration. And we somehow split them to be two functions sitting at the two ends of our line network. And so this is how we show that you cannot beat this upper bound. Okay. So to pave the way for the asynchronous operations, I have introduced some absolute time it takes to complete one step of computation. So that's tau comp. And then the absolute time it takes to complete one round of communication, that would be tau com. And so in a synchronous mode, you want to wait for everyone to complete a computation step, then everyone to complete a communication step. And in real systems, the speeds would be very different. And this is why there are weaknesses of these synchronous approaches. And you really want to go to asynchronous operation. Okay, so that's what we do now. Okay, and we'll have the following model of behavior in the asynchronous operation. So we'll assume that the edges in our network activate independently of one another. So there's no more a notion of a synchronous step. And we'll take as an algorithm the following approach. We'll assume that communication is triggered between U and V at random times, and those random times will be the points of some Poisson process that is specific to this edge. And so PUV for us will be the frequency of this Poisson process. So in this setup, we redefine slightly the complexity of communication. Now this will be the reciprocal of so that comes next. When this activates, they exchange some gradient information. So we would assume that we have a network that is reduced to a single link, and we would do very much like what we have done in the synchronous mode, but for a network that is degenerate and reduced to a single edge. That's exactly what people would, the two agents U and V would do upon activation of their edge. They would exchange their dual gradients. And so this is exactly the previous operation for the first order gradient descent if the network is reduced to that edge. Okay, so what we can show in that case is a guarantee with, so that's if you like the asynchronous version of a first order gradient descent. So we can show there is exponential convergence with a characteristic time that behaves like kappa comp again times kappa tilde comp. Okay. And notice that now this is a randomized algorithm because the activation times, they are random. So this is why in our guarantee, we have an expectation that appears. So that's the non-accelerated case. And it has puzzled people for a long time, the question of accelerating asynchronous network averaging or asynchronous distributed optimization. There had been proposals, but with no proof of acceleration, except for specific networks. So there's been interesting work by Alex Dimakis at UT Austin, where he came up with what he called geographic gossip, where he could accelerate network averaging using the geometry of the graph in some very specific way. So we'll see that we can do acceleration in this asynchronous setting without any specific construction relative to the network at hand. So this is, in fact, a continuous, asynchronous version of Nesterov acceleration that we have here. So we want nodes to maintain two vectors, not one. And the logic of the scheme is as follows. So between updates, a user, V, holding vectors YV and ZV, lets them evolve according to an ODE, bringing them slowly together. Okay, that's the ODE that is written here. Whereas upon activation of an edge, again at some random instant of a Poisson process, they update their individual vectors by exchanging dual gradients based on their Y variables. So this is the kind of update. And they do that for the update of both of their vectors. So there are two gain parameters involved, but the logic is very similar to the previous one. And this is somehow a version of an Nesterov's acceleration, but tailored to this continuous time asynchronous framework. And so what we showed is that by picking the gain parameters correctly, we can indeed get an improved exponential rate of convergence compared to what we have in the previous scheme, where we do apply a square root to the condition number we previously had. So that's the flavor of the guarantee we get for the speed of convergence. So some remarks about this scheme. So we coined this, yes? So it is affected indirectly because between two updates, Z and Y are pulled together. And so this is a little bit like what we had in the previous Nesterov scheme. So except that I might have flipped the two notations, but you have a similar flavor. So the ODE would be the equivalent of this. Yes, well, actually, the logic we started from was similar, then we massaged it to arrive at the version that I described, but we started from the same logic. Okay. So what I wanted to say about this scheme was the following. So we coined this a continuized approach. So this is in reference to something that David Aldous proposed for analyzing discrete time Markov chains. So he created continuous time Markov chains, allowing him to analyze the discrete time chains, and he called them the continuized chains. So hence the terminology. And what we mean by that is that they apply to some schemes that are discrete in nature. So we wait for some continuous time. Then at the time where we want to do an update, we may solve the ODEs for the values that are involved in that update, and we do a discrete change. So this is really something that you can implement in discrete stages over continuous time. But the analysis we do is essentially in continuous time, and this is a nice analysis because it involves differential calculus leveraging the properties of the Poisson process. So we cook up Lyapunov functions for our dynamics, and we show that they converge exponentially fast to zero using differential calculus, and this can be done thanks to the Poisson process driving those dynamics. So one interest in those schemes is that there's no synchronization step. So implicitly, though, we assume that all the agents measure the speed of time like they have synchronous clocks, so to say, because between two updates, they have to measure how much time has elapsed, and that must be consistent across users. So implicitly, we assume their clocks are synchronized, but that's not a big assumption. Another remark is that this scheme, so we developed this scheme for the purpose of asynchronous distributed optimization. But then by discussing with our colleagues, Francis Bach, Raphaël Berthier, Nicolas Flammarion, so experts in optimization, they realized that when you bring it back to the discrete steps, you can interpret it as a two-sequence schemes, just as Nesterov's scheme, but where the weights are random, involving the time elapsed between instants in your Poisson process. So even for a single agent's optimization, this produces a new accelerated scheme with randomized coefficients. And the proof is somehow a bit nicer than the original proof of Nesterov's acceleration, where the choice of the gain parameters is a bit subtle. Here, the continuous time analysis makes it a bit smoother. Okay, and finally, well, this acceleration does matter because, again, for network averaging on a cycle, we could get improvements from n squared to n for the characteristic time of optimization. So that is quite significant. Okay, so that's, yes. That's the same agent. So the same agent holds ZU and YU. They have been updated at one point. Then sometime later, agent U needs to interact with a neighbor. So at that point in time, it can solve the solution of the ODE and say, okay, ZU and YU at the current time must be this. And now I do the updates, compute the gradients and so forth based on these updated values. Yes, so the thing is implicitly, so you see if I drive this, so two nodes interact at one point, then they decide to re-interact later on. We want them to have solved the same ODE with the same elapsed time between the two updates. Well, that's our analysis applies to that case. So this is what I was meaning. Sorry. Yes, so which parameter? Yes, so I'm sorry, I can't give you an insight. Now I don't remember the details. So it is, yeah, it is essential to get the acceleration to work to pick all those parameters right, but I won't give, I will say silly things that I don't remember. But the point of the analysis is that you can pick them in a not so painful way. But, I don't remember how that looks like in the end. Okay, so what I want to talk about next is about the more realistic modeling. So in a real system, when you decide to compute a gradient, then it might take some time. When you decide to communicate, maybe there's some latency in the communication link between two agents. So we wanted to incorporate those time delays in our model and try and come up with schemes which can cope with those delays, because it's quite well known that time delays in feedback loops can have huge effects. So it can destabilize widely some systems. So that was our interest in this part. We have the following model for the operation of the system under delays. We will have an assumption that when node U decides to compute a gradient, the computation will be completed in time at most tau sub U. So that's the compute delay parameter for node U. And so we'll assume that node U will trigger compute updates again at a random instance. So the points of a dedicated Poisson process, and P sub U will be the frequency with which you do compute gradients at node U. Likewise, for communication, for a pair of nodes UV, we'll assume that when they decide to communicate, the communication will be completed by some time tau sub UV. So that's the delay characteristic of communication between those two nodes. And again, we'll assume communication updates will be attempted at the instance of a dedicated Poisson process. And so parameter of interest P sub UV will be the intensity or the frequency with which those updates occur on average. And so tau sub U and tau sub UV, this would be given to us. That would be the physics of the system. P sub U and P sub UV, these are our choices, just as the use of a Poisson process is an algorithmic design choice. Okay? And so I won't talk about accelerated convergence, but I will talk about convergence using what would be the equivalent here of a first order method. Nevertheless, each node will maintain two state variables in the scheme I'm going to describe next. But this is not for the purpose of acceleration. This is for the purpose of teasing apart computation and communication. So that's, well, the scheme itself will be a bit of a mouthful, so I don't expect that the scheme will help you much, but at least you'll get a flavor for the kind of, at least the kinds of updates it involves. So communication first. So assume a pair of nodes U and V decided at some time t minus tau sub UV to communicate. So we know that the communication will be complete by time t. And so what we assume is that they would decide to exchange their z variables as they were at the time where they started to exchange, so at time t minus tau sub UV. And they will update those variables when an interval of time of length tau sub UV has elapsed. So at time t plus, they will increase their variable by an amount that depends on those variables at time t minus tau sub UV. And there's a gain parameter in the update that involves the reciprocal of the frequency of the updates. And on the numerator, I have some gain k sub UV. So morally, the average magnitude of the gain will be KUV over PUV times PUV, the frequency with which you do updates. So KUV plays the important role of the average gain with which you inflate, you magnify the updates you do. Okay. And we have a similar kind of logic for compute updates, which is a bit more painful to parse, but okay, so there's a bit of something I don't want to describe too much. You have to subtract a bit of the strong convexity to your function fu, then you look at the convex conjugate of that modified function fu, which is called gu. And then if node u decides at time t minus tau sub u to do a compute update, then the output of this compute update will be a dual gradient of this function g evaluated at its variable z at time t minus tau u. And so once this compute update is done, which is certainly the case at time t, it updates its z variable and y variable using these quantities that have become available at time t. And so as for the communication updates, we'll have gain parameters here, which are of the form Ku over Pu. And so Ku has the meaning of the average gain with which we multiply the additive terms we add to our variables based on compute updates. And so our scheme, as I said, it had as free parameters the frequencies with which we do updates. It also has as free parameters the gains Ku, Kuv that we have the freedom to choose. And so, as I said, in systems with feedback, when there is time delay in the feedback loop, you cannot choose the gains arbitrarily large. Otherwise, we will have oscillations. And so I guess the real life example of that is when you're trying to tune the temperature of your shower. You try to do it very quickly. So there's a delay in the feedback loop. And so you will oscillate between very hot and very cold if you are too aggressive. So, and the folklore rule for delayed systems with feedback is that you should tune the gains to the reciprocal of the delay in the feedback loop. And so we'll see we need something of that kind, which is this assumption A here. So, well, it's a bit more complex than just tuning the gain parameters to the reciprocals of the delays, but still it has this flavor. So essentially, KUV, you want to make at most 1 over tau UV, and in fact, a bit smaller than that. Same for the compute updates. Ku, the gain parameter for the compute updates, needs to be taken at most 1 over tau u, but in fact a bit smaller than that. Once we enforce those conditions, we'll be able to have a result. And this will be expressed in terms of the second smallest eigenvalue of the Laplacian of our graph, weighted with the gains KUV, okay? And so the result looks like this. We have, again, exponential convergence of our variables to the optimal model with a characteristic time that does depend on this lambda 2k quantity. So the precise dependency is this kappa comp over lambda 2 of k. And you have other dependencies. So it's expected that you cannot have a characteristic time that is smaller than the largest delay of all the delays you have in the system. So that's something that will always show up. And then there's something that is specific to compute updates. But let's focus on this one instead. Okay, so that's the result we have, and I'll discuss a little bit some of the implications. So computation, that's the job of a single agent. It decides at one point to launch a gradient computation. And so we know the gradient computation will be completed by some time. And so this will be a gradient computed on a variable that was specific to that agent at the time it started the computation. But it might have had additive updates to its state variables between the time it starts computing the gradient and the time it completes. And so by the time it completes, it's a gradient of something that is a bit outdated. And so the whole point of this choice of gain parameters is to make sure this does not compromise convergence of the dynamics to the desired target. Okay, so like the previous asynchronous scheme, it's implementable in a fully asynchronous mode. It also requires synchronized clocks because the times at which the updates are logically met when there is communication. So in the logic I described, we want to wait exactly tau sub UV. And so they need clocks that are synchronized, but that's not a big deal. more importantly, if you had those delays in communications and you decided to optimize using a synchronized approach, then you would do one communication stage. This would terminate by the time all communications have taken place. So this would be driven by the largest of the tau UV. And instead of having a time constant that is like a max of tau UV times the spectral characteristic of the Laplacian, we instead have a spectral characteristic of a Laplacian weighted by the individual delays, and this can be much more advantageous. And this is what we call the asynchronous speedup. And another remark is that this condition A that I was flagging here, this is in fact the same as saying that the spectral radius of a matrix that is linear in the gain parameters is less than 1. You could view that by having the P parameters as candidate eigenvectors. And so you multiply by the denominator and you find some equations. So it's a bit of a manipulation, but so you have this equivalent description. So this is in particular a convex constraint. Using this framework, we can say, okay, if I go for those algorithms, how could I tune all my parameters? Maybe I want to maximize speed, so I want to maximize this lambda2 of k. That's an ingredient in my characteristic time. And so speed maximization can be cast as a convex optimization problem. So maximizing the second smallest eigenvalue subject to a spectral radius of a matrix linear in K being less than 1, that's something that is a convex. And so you could go about it by solving this. Once you have a solution, say well, 1 is problematic, so you would want to take 1/2 here. You solve for this, and then you use P quantities that satisfy this, and then you are all set. So that's one approach. There's another approach where you are concerned not just by speed, but also by energy consumption. Then the P parameters play a role because quite plausibly, the energy cost will be proportional to the number of updates that are made. So let's say the communication, for instance, the communication cost per time unit is proportional to some linear function of those activation frequencies, P sub UV. So what you could do is try to trade off speed for energy. And so that makes for the another strategy. So this is what I'm describing here. So you could set your gain parameters K according to this assumption A, and then try to maximize over the activation frequencies P, the speed, lambda2 of this Kp, minus something that captures the energy cost. So this is no longer convex, so you must solve it by other means, but okay, there you can do a brute force search. And so what I want to do last is report on some experiments we did with that. So we started with networks on the left. This is a complete network with random delays. And I'm focusing on network averaging, so there's no fancy computation involved. What I track here is the number of edges, the lambda2 capturing the speed of convergence, and then this energy cost, which is I'm taking given by the sum of delays times the frequency of activation. And so if you run this optimization, typically you get sparser networks. Here you get a faster convergence rate and a smaller energy expenditure. So we have a nice scenario where sparsifying a network makes it better in all respects. And this is a bit reminiscent of something that is known in road traffic networks. That is the Bryce paradox. So for those who don't know the Bryce paradox, this is the fact that if you suppress a bridge or a road in a city, then you can make traffic better for everyone. And so there's a nice theory illustrating that. And there are concrete examples. I think a bridge in New York was a concrete example of that. When it was closed for works, all of a sudden the traffic flowed much better in the city. So we seem to have something of that kind here. And this is just another example with a, okay, time's out, so I will conclude. But this is a same story, except that we get a sparser network with a slightly slower convergence rate, but a much decreased energy. And so, okay, so I guess that, well, this work I was reporting was really driven by the desire to have models that captured some specific aspects of actual systems, and time delays and asynchrony are, I think, quite important. So we really targeted that. So that was the purpose. There are many interesting questions in that space of distributed learning and optimization. So here I'm mentioning a few. I've already alluded to those in the beginning. So privacy is an interesting one. So for instance, guarantees such as differential privacy you could try to have. And then you would not want to share your gradients in clear with your neighbors. So there are solutions where instead of sharing your gradients, you share noisy versions of your gradients. And for this, we have started obtaining guarantees on the privacy that you can obtain. And as usual for privacy studies, there's a trade-off between the privacy guarantee and the loss in utility. And so we have interesting trade-offs of that kind. I mentioned also personalization of models. So there are theoretical works on that. For instance, if you have agents that have their own data set, but there is a notion of proximity between the distributions of the data sets of the various agents, then at least in the early stages of the optimization, you can, as an agent, leverage gradient computations of agents that are statistically similar to you. And you can speed up the early stages of the training, even if you are going for a model that is targeted to your own data rather than a common model. And unsupervised learning is also a rich mine of problems in that. Okay, and I'll stop here. Questions? Yes.
Yeah, I have a quick question on the slide where you showed Bayes paradox. Yeah. I missed something. So I didn't understand what are the graphs on the second row, starting from the first.
So I start with an initial graph. So for instance, here it's a complete graph where I pick P are all equal to 1. And the delays, I think we picked uniformly at random between 1 and 2 or something like that. And so now we let the P evolve so as to minimize, well, maximize the function like that. So trying to get a good trade-off between speed and the energy cost that we measure by this. And so that we have some kind of brute force search over P parameters. And we also consider suppression of edges. And so as we do the brute force optimization, we find some configurations which have far fewer edges. So here we have gone from 400 plus to 122. And the speed of the scheme we propose then, once we have tuned all these parameters, this is driven by some lambda 2, which is larger. So this is a faster convergence. And also our measure of energy cost is decreased. So we get the best of both worlds. So faster convergence, sparser network, and a smaller energy footprint. for the first part of the talk, yes. So we have indeed some results. So some of the results we have were for not stochastic gradient, but finite sums when each agent's function is of finite sum structure. So there, instead of doing full batch for FU, you may want to do a single sample or mini batch. And so there is a very nice abstraction that Adrien Hendricks came up with. He has this notion of an extended graph. So you have the communication graph, and then he has a compute graph. So let's say U, node U has a samples theta 1 extra theta NU. And so it's a neighbor of V, which has a samples theta V1, theta NV. And so you may transform this into a network where you have NU dangling nodes. And so you have here NV. And so the gradients, so here that would be L of theta 1 x, the loss function corresponding. And so you can really take the analysis we had for the full batch, but do it when the full batch is now one single sample, and you can do acceleration and all that using the results. So we have such an extension. So that's not exactly the stochastic gradient, but we also have some works on stochastic gradient. Not all of them we tried with the stochastic gradient case. Those we have where we really went for stochastic gradient was for a personalization of models, where we had a notion of proximity of distributions, and we assumed the stochastic gradient sampling at the agents rather than a fixed function. You mean suppressing edges? Okay, so maybe I was hiding a bit something here. There is, in this constraint we enforce here for the gains in communications, you need to slow down how aggressively you update at edge UV based on the delay in the corresponding edge UV, tau UV, but also the delay in the neighboring edges, tau U prime V prime. If U prime is equal to U, then this plays a role also. And so there's an example where you can understand why this is harmful. This is when you have a line network with unit delays going from one neighbor to the next. And then you also have a shortcut, closing the loop between the first and the last, but this is a much longer delay. So the gains in the short edges, those at the ends of your line, they would be affected by the delay in the long shortcut. And so that would let you take low gains and so a slow optimization. So if instead I kill that long edge, then I can take larger gains and I get a better optimization. So in fact, all the quantities would change if I give myself the freedom to suppress edges. So in our optimization here, where is that? Oh yes, here it is. We also have the freedom to set P to 0, which is the same as suppressing an edge. So it's really convenient to write down differential equations for the evolution of the Lyapunov functions we have. So that the Poisson process will buy you that. We can do something more with the Poisson process, but then not taking all the events of the Poisson process. So in fact, we have an extension where we allow for sharp constraints on how many computations in parallel a node might launch in a given time interval. So that's how you would express, a limited compute power. You can launch perhaps one gradient compute at one time. So if you have launched one and then your Poisson process tells you to launch a second one right after, we can just suppress that point. Okay? And so we have more refined conditions when we incorporate those capacity constraints, both for communication and compute.
There's no more question. We can thank Laurent again, and we restart at 2:30.